So, welcome back again. So, in the discussion of evolution equations, so far we have seen heat equation and wave equation, and now we are some discussion on Schrodinger equation. This may be new to many of you. So, let me just begin with a brief discussion of this equation. So, this is from quantum mechanics. So, it is analogous to the Newton equation for quantum mechanics. So, it describes the dynamics of a quantum particle. Okay. So, let me first write it in as you see it in a physics book. So, this equation okay, just let me write that s square by minus 2m Laplacian psi plus v psi is equal to this I comes. So, this d psi by dt. So, v the real valued function. So, so this is called potential. Okay, so, h is the Planck's constant. Okay. And this m is mass of the quantum particle. So, soon we are going to absorb everything in so make it everything one, mass of the quantum particle. So, unlike the Newtonian mechanics, the particle need not we can only say that the particle will be at some position x with some probability. Okay. So, this psi x t called wave function. So, the physical meaning of that, this psi x t square. So, this denotes the probability of the particle, that quantum particle being at position x at time t. Right. So, that is the physical meaning of this wave function. So, since the particle has to be somewhere, okay, so obviously we expect this psi x t square should be 1. So, this is in okay, physical space. Let me. So, most of my discussion is only in R3. Okay. So, that is a physically relevant thing. Of course, mathematically we can do it for any Rn. Okay. So, if initially this wave function satisfies this equation, so this should hold for all t, right. Okay. So, obviously already it said that we should expect a unitary operator. Okay. So, that is already hidden in this physical statement. Okay. So, now we are going to absorb these constants, Planck's constant and the mass, everything, and consider this in the simplified form. So, we consider this Schrodinger equation in the form. We consider the equation, Schrodinger equation in the form. So, you can all absorb them in either t variable or space variable. Okay, so here I am assuming, so no potential. So, the particle is no, there is no barrier at all. Potential function means, so there will be a barrier, so there is some resistance, but here it is a free particle. Okay, first let us study that. So, it almost looks like heat equation, but for this factor I, okay, just I. So, let me begin with again a Fourier transform treatment. So, we can see a similar thing to the heat equation, but it is different, very different. Okay. So, formally you take the Fourier transform, partial Fourier transform only with respect to x variable. So, this is 1 by I. So, d by dt of u cap is equal to minus mod j square u cap. Okay, and then you this ODE you solve. So, you get u cap j t e to the minus I t j square u cap j. So, this is u cap u 0 is the initial condition. So, get that. Only thing is there is I sitting here and this function. So, consider this function. In fact, this was discussed in our first part of the course. Consider the function e to the I x square. Okay, let me just say that t is only a parameter. Okay, so, this x in R n. This is only a bounded function, of course smooth, but this is not in the Schwarz space. Okay, so, Fourier transform and other things cannot be readily taken, but this is a tempered distribution and that is good for us. This is a tempered distribution. So, you may refer to our first part of this course, okay, where in fact compute the Fourier transform and other things. Okay. So, this is good enough, so that we can take Fourier transform, inverse Fourier transform and etc. Okay. So, we can still play with this function, though it is not in the Schwarz class, okay, but it is a Schwarz distribution, that is fine. Okay. So, here I just write that. So, you just recall from the first course. Okay. So, we have, in fact, let me write. So, this is also a good exercise for you. The Fourier transform of this exponential I x transpose A x. So, this is most general, okay, that's of j. So, this is for so, remember this is only a tempered distribution. So, we have to again this constant of pi may vary depending on the Fourier transform you use. This is determinant of A e to the I pi n by 4 exponential is similar to Gaussian. Okay. So, very much similar to Gaussian, but only with this factor so, where A is a symmetric positive definite matrix. Okay. So, we have the Fourier transform of this function and inverse, because inverse transform is also the similar thing, right. So, we can do that thing. So, put all these things together, these things together, to get. So, let me just write that u x t this you may not see in many books, but I am just writing it e to the minus I pi n by 4 integral r n exponential I mod x minus y square. So, it is convolution, but convolution with a tempered distribution u 0 y t y. So, I am just taking here, since we are dividing by t. Okay. So, I will not go in further discussion of this formula, but it is you can read the literature more about it. And so, but I just stated here because it looks very similar to the fundamental solution of the heat equation. So, and that Fourier Poisson formula very similar, but for this factor I. So, this even interpretation of this integral you have to be, of course, this is a bounded function, there is no problem, but you have to be, when you want to take L2 norm, you have to be careful. Okay. So, I will not go further into this formula. So, back to our semi group theory. So, again we want to approach this Schroedinger equation through this semi group theory. So, first I consider this without potential. Okay. So, just in appropriate domains, and then we consider with this Laplacian plus potential. Okay. And here we apply the Carnot's perturbation result to conclude that this this operator. So, this will be a multiplication operator is qualitatively similar to the one with without potential. So, whatever Laplacian, whatever property the Laplacian will have, the same thing will have for this Laplacian plus v. Okay. So, that is what would like to do. Okay. So, let me begin with the simple case. Okay. So, I just work with R3 and our main space is L2. So, again let me not write R3 every time. Okay. And we consider this Laplacian operator. So, again just look at that equation. Okay. So, this we have to study this operator. Of course, that we have done many times, but let me again repeat that. So, Laplacian with domain equal to H2. Okay, natural one, right. This L2 is necessary because, as I said, that denotes the probability. Okay, let me again say that. So, this for the wave function, this denotes the probability of the particle being at position x at time, and we expect this, and okay, this that is L2. So, these are dictated by the physical requirement. Okay. So, this is the setup. Okay. So, let me start with this proposition. So, let me do it in somewhat detail, so that you can imitate the same proofs wherever I have left them. Okay, this the linear operator Laplacian with domain H2 is a self-adjoint operator. In L2. Okay. And that immediately, once we prove that proposition, that immediately implies by Stone's theorem I Laplacian generates a unitary group. Okay, and I is coming from the Schroedinger equation itself. Okay, so let me again show you that. So there is I there. Okay, so that it's sufficient to show that Laplacian is. So there are several steps. So let me just prove. Okay, so the domain of Laplacian is H2. H2 is clearly dense in L2. So this first part is very clear. So delta is a densely defined closed operator. Densely defined closed operator. Okay, so this densely defined is straightforward because 2 is in. Let me just show you because these computations we have to do many times. So let me just show this part closeness. So again recall the definition. So let f k be in the domain of the Laplacian, that is H2. Okay. F k converges to f in L2 and Laplacian of f k converges to g in L2. So what we have to show is to show f is in H2 and Laplacian of f equal to g. Okay. Of course, everything is in the weak sense, this Laplacian, but once you show that, so how do you prove that? Okay. So let me just, so take any test function, take any phi in C C infinity, okay. Then so this integral f k phi, this converges, f k converges to f in L2. So this is converges to f. Okay. But this, since f k is in H2, so this also is let Okay, that's okay. And also we have this Laplacian f k phi converges to g phi. Okay, but this one is f k Laplacian phi. Okay, and then Laplacian phi is again a C infinity function with compact support, and that converges to f. And now if you look at these things, okay, so just conclude that f is Laplacian of f equal to g in the weak shunts, but g is in L2. Okay, so that means Laplacian, the weak Laplacian of f is in L2, and again use Fourier transform just to conclude that H2. Okay, so the arguments are not always straightforward, so they are using several properties. So you have to do them carefully. Okay, so next we show Laplacian is symmetric. Okay, so that is Laplacian f g. So this is L2. Okay, so let me write that. So this is f Laplacian g for all f g in H2. So that's the domain of Laplacian. Okay. So again you begin with smooth functions. So because that's how we generally do. So for smooth functions, because we can integrate by parts and there are no boundary terms for smooth functions phi and psi, when I say smooth, they are C infinity. We have Laplacian phi psi is equal to, I can integrate by parts. So that's right. And similarly, and phi Laplacian psi is minus psi. So that shows. So for smooth functions we have this relation. And next to use density to conclude that is symmetric. So we have a densely defined closed operator which is symmetric, and in order to conclude Laplacian is self adjoint, we need to show plus or minus I belongs to the resolvent set. Okay. So that means, so for any f in L2, we should be able to solve this plus or minus I. There should be a solution of this. Okay, so we should find u in H2 satisfying this. Okay. But again this is our familiar Laplace equation, you have seen it umpty number of times now. So, again you take the Fourier transform. So, that is one strong tool, you keep on using that. So, this taking Fourier transform, what we get? So, this is plus or minus I u cap minus, this is minus. Okay. So, formally, informally, okay, this u cap is defined by this. And because this is complex, we are saved. So, this denominator is never 0. So, you can again take this and show that it is NL2. So, indeed we get. So, this is slightly different from what we have seen earlier, but because now there is a complex coefficient, but that is fine. Okay. So, we will find that. Okay. So, moreover, okay, let me just okay, that is the one thing. And okay. In fact, you can also start with F smooth, and then you show that this, in fact, it is sufficient to show that the image of this, okay, if you again look at the general theory. So, conclude okay, this is sufficient for us, image of plus or minus I minus Laplacian is L2. Since we already have closeness and symmetry, even in fact it suffices to show that this image is dense in L2. Okay. So, for that you just need to take these smooth functions and work out this, okay, by taking the inverse transform. Okay. So, final conclusion. So, just conclusion is that the Laplacian is self-adjoint. So, again go back and see the topic in unbounded operators. So, when a closely defined densely defined closed symmetric operator is self-adjoint, okay, there are very simple conditions for that conclusion. Not all symmetric operators are self-adjoint, so bear that in mind. So, you have to do little extra work. Okay. So, therefore, this I Laplacian generates a unitary group. So, call it, again I will denote it by UT. Okay, and we obtain a solution of the Schroedinger equation. Obtain the solution of the Schroedinger equation this is without potential, Schroedinger equation. So, 1 by I del u by del t Laplacian u as u of t is equal to ut of f, and of course, we have to take f in the domain of the generator. So, f here it is H2. Then we get a strong solution, okay, and we have this norm of u in L2 same as This is one requirement from the beginning we are discussing. Okay, so this, so UT is a semi group, UT is a unitary group in L2. Okay, that's important. Okay, so I stop here, and in the next class we consider the Schroedinger equation with potential, and for that we apply Cart's perturbation result. Thank you.